All right, so we're going to talk about curve sketching. So something that you guys all know something about. Where I see this lesson as a way to, like I said, to get back into doing math, practice some algebra, do some derivatives, thinking graphically, just a kind of an easy way to get back into doing things. So, if we have some function, and a rational function, a radical function, some kind of function, we have no idea what the graph looks like, the graph of this function. What tools do we have to analyze, to get an idea of what we might be dealing with this function?
Critical points.
Okay, that's a good one. And the critical points, just to be more specific, what are we looking for here?
Well, I'm thinking there's intersections, there's spots where it's zeros, there's black points where the derivative is zero.
Okay, so let's list some separately. So critical points. If we're talking about critical points or points of interest, what was the first one? Intersections?
Yeah, that's what I think would probably be.
Like intercepts?
Yeah, if we're going to be sketching the curve, I think that's probably about the intercept of all those.
So finding the intercepts, x and y intercepts, that's a good place to know where it crosses our axes. What else? Inflection points? And how do we figure out about those? Second derivative, okay. Second derivative is 0 or, so let's just leave it at that. If our second derivative is 0, so we're looking at the second derivative. What else? What do we do before our second derivative? First derivative, okay. So if f prime is 0, what else can we? Any other critical points we might be interested in? Points of interest on our graph. Anybody think of anything else?
Holes.
Holes? Okay, great. Okay. We have some kind of rational function. We're interested in asymptotes. If we have rational functions, we're interested in holes. So those are good ones. Would be good ones to look at. What can we be? Let's see. What do I want to ask here? Let's leave it at that. Anything else? What else can we think of to analyze a graph? Minimums and maximums. So the first derivative can tell us we're interested at where the first derivative is 0, but we also want to know, are we up here, are we down here? So we want to look at a minimum or a maximum, so we want to analyze for minimum and maximum. So we have a lot of stuff here so far. What else? Think more along the lines of, less along the lines of calculus, more along the lines of algebra. What?
Slope in a region.
What's that?
Slope in a region.
Slope in a region. So we want to know if it's
Positive
or negative, increasing, decreasing. Okay, that's a good one. That's another good way to find out about what it looks like. Derivative functions, right? So we're looking at the sign of the derivative, basically.
And second derivative to see if it's curving up, down.
Okay, so with the second derivative, rather than just inflection points, the second derivative can tell us about the concavity. Is it concave up, concave down? So that's another good one. Anything else? Anybody think of anything else?
If it's shifted, like off base, like a parent function.
Okay, good. So we can use our knowledge of families of functions. So if we know something about a family of functions, we know what we know what a parabola looks like. So if it's shifted, that'll give us an idea of what our graph looks like. So I'm going to call that knowledge like families of functions, knowing what certain functions look like. So if it's not too complicated, then we can get an idea from that. Any other ideas? Yeah. Plug in some x values and get an idea of what it looks like. Okay? So if we say if we knew where a maxima was and we knew where an asymptote was, but we wanted to see what it looked like in between those, we could plug in a few points. So plug in numbers. And then I would do a few other things before I plugged in some numbers, just to have a better idea. But you could just plug in a bunch of numbers and just plot points and get a pretty good idea of what it looked like. But that would take a lot of computation, especially if you have a complicated function. What else? Think along the lines of the asymptotes. What kinds of asymptotes can we have? Vertical or horizontal? Or slant. What do the horizontal asymptotes tell us in general? Something over something else. What?
The degree, which part of the function is the higher degree?
So which part of the function? I'm thinking more. Everything you're saying is correct. I'm thinking more. Does if we have a graph here and we have a horizontal asymptote, does the horizontal asymptote tell us what the function's doing here? No. What does it tell us? End behavior, right? So the horizontal asymptotes you can think of at the end behavior. So I was kind of going for limits at infinity. What happens at infinity? And that the asymptotes tell us about that. Sometimes we need to think in a little more detail about the limits at infinity. Like you said, we can have a horizontal asymptote, we can have a slant asymptote. So we're interested in how it goes to infinity. So our limits at infinity, we've got a lot of them here. Anybody think of anything else? How about if we're thinking of families of functions, what kind of functions give us nice behavior that how do I want to ask this without giving it away? How about periodic functions? If we know their period. So if we have a trig function that we can analyze, sometimes we can analyze a graph based on its period. So we can say, okay, I know the period of this function is 2 pi. I'm just going to look at one period and know that it repeats. So if we have a periodic function, that can help us out. And that also has to do with families of functions. And did you have another idea? Even or odd, okay. So symmetry, even, odd. That's a good one. So we have quite a list there of ways that we can analyze a function. We're not always going to have to do all of these to graph a function, but these are all tools that we have available to us. There were a couple of others that I had written down. We can look at the domain and the range. So if there's some restriction in the domain, that will tell us something about what the graph looks like. And the range might have to do with with the asymptotes. But we also might have, if the domain is restricted, that might restrict the range of the function as well. So that tells us where the graph is going to start and stop. And what else? I also, in my little notes, I mentioned if the function is differentiable, if it's continuous. So if we have discontinuities, that's another way that we can look at a function. What we're going to do here, and just in general, what I would be looking for is some kind of subset of these. So what I would suggest, if we're analyzing functions, if we're going to graph a function, your powerful tools, or your go-to tools, you want to find the domain and the range. That's where I would start. Make sure there aren't any restricted values, anything like that, anything that's going to give you a problem. I would say the intercepts and the asymptotes are extremely important. And these we can all do without calculus. Which is nice, but it's nice to be able to use calculus. So then we're going to find our critical inflection points. So we want to know our f double prime, f prime equals 0, or does not exist. And from these we can find the extrema. And these are usually going to give you a pretty good idea of what your graph looks like. So let's go through a couple of things here. Since we have our books, everybody has our books, let's look on page 216. They're very quiet today. So we're looking at page 216, number 52. So just to get us thinking graphically here, we have a graph there of the first derivative. And we want to use that to sketch a graph of the second derivative and the function itself. So what do we want to do here? So I'm going to draw a quick sketch up here. So we're on page 216, number 52. So here are my axes. This isn't going to be perfect and beautiful. Just give us an idea of what we have. So our function looks something like this, or a derivative function, right? And we have a dot here, there, and there, and this is at...
Both open at x equals -1.
Oh, both open? Okay. There we go. So this is at -1, and this is at 1, and up here we're at 2, and this is at -2. So there's an idea of what our graph looks like. So what do we want to do first? We want to look at the function or the second derivative? Second derivative? Okay, that looks pretty easy. So for f double prime, what do we know about f double prime?
It's going to be undefined at -1.
It's going to be undefined at negative 1. It's going to be undefined at 1. Right, right. For x less than negative 1, what is the second derivative? 0. F prime equals 0. For x less than negative 1. How about for x greater than 1? Or greater than 1. 0. How about between negative 1 and 1? Is it 2?
Yeah.
Okay. Equals 2 for x between, I'm going to say, negative 1 less than x less than or equal to 1. And I guess. Okay. So what is this graph going to look like? So here's our axes. Whoops, I'm going to do that in black. Oh, do the axes in red, and we'll do the lines in black this time. So for x less than negative 1, what do we have? A flat line along the axis. So we're going to have something like this. And that keeps going this way. And for x greater than 1, what do we have? Same flat line going the other way, right? So we have open points here. And then between negative 1 and 1, what do we have? So up here, and I made my lines a little long, but like so. So that'd be my graph of my second derivative. Let's see, what did we write?
It wouldn't be good for the fact that it does not exist. It's not the vertical point.
Right, so should I have this?
Yeah.
Yeah. It's the first day. All right, so now, yeah, this is for me to get back in here also. So there's my second derivative. Now this is f prime. How about the function? We want to do a graph of the function. How are we going to do that?
We're assuming we have
Well, we're replacing the derivative is constant w over slope line.
Okay, so where the derivative is constant, we have a slope line. So what is our, and we don't need to do a perfect drawing. We're sketching. So what's our slope here for x less than negative 1? Our slope is 2. So we have a line with slope 2, right? So here's my line with slope 2. And I'm going to put there we go. Like so.
could be closed or it could be open.
Could be closed. It depends on what we do on the other side of the interval also, right? And then up here, for x greater than 1, what do we have? A line with slope 2. So here's my line for x greater than 1. Line with slope 2. And I'm going to put
How big is the derivative equation using this? Talk about that. No, wouldn't it also have been just taken out by the fact that we've got the whole curve going on? Creating your stuff that you couldn't have all both. Or actually, no, you could have a limit.
yeah,
on both sides.
the limits are equal, right?
Yeah, you could have the limits equal.
Right.
And you have the function.
Right. All right, and in between those 2 points, what do we have going on in between these 2 points? A parabola. And we could figure out the equation of the parabola, right? Because what's the equation of this line? Y equals 2x. So y equals 2x is the equation of this line. So we need, that's our derivative, so our original function is going to be y equals x squared plus c. We're going to say, I'm saying that these, because it has to match up with these, that kind of fixes our constant, because it has to match up with these graphs. So our parabola is going to look like something like this. I didn't make it connect there at the origin. So we have our graph looks, and I'll put the dot there. So there's our graph of our f. Make sense?
I would just sort of normally attach with the same slope and then sort of put a parabola extending out to that line. And,
right. My sketch is not beautiful, like I said, but if it were beautiful, that you're right, the parabola would connect smoothly here, so the slopes would be the same at that point. All right, good. Let's see. Let me look at. Let's look at a couple of others on page 216. Number 54. Well, number 54, it gives us some conditions. It says f of 0 equals 3, and 2 is less than or equal to f prime of x less than or equal to 4 for x in this interval -5 to 5. And our question is, what's the greatest and least possible values for f of 2? So we don't necessarily have to go through the entire procedure, but let's think about how we would go about this. We have a value of function at a point, and we know the maximum and minimum possible derivatives in this interval. So we want to know what would be the maximum and minimum possible values for f of 2. How would we go about this? What do you think, Brad?
Well, you have this slope,
Okay, we have a slope.
so you find the minimum slope to get the least value and the maximum slope.
So you're saying from that point, use a minimum slope,
Yeah.
make a line to the other point to find the greatest value to the maximum slope. Okay, perfect. So I'm not going to go through the whole process. Everybody understand what we said there? To find the minimum value, we would use the smallest slope and connect those 2 points with a straight line with that minimum slope. And to find the maximum value, we'd connect those 2 points with the line with the maximum slope. Because it doesn't matter what our function does if we have these 2 points. If we have f, we're looking at the function. It doesn't matter what it does in between here. It just matters how it goes from one to the other. So the maximum slope is going to get us there, get us the maximum value. The smallest slope is going to get us the smallest value at that particular value. You like my? Yeah, it doesn't matter what the function does in between here. It can do whatever it wants and end up here. It's not going to be bigger than if we use the maximum slope. Okay? Is that clear, everyone? Everyone's good? Are we getting back into thinking about graphs and how they work? We just have a couple more minutes. So I have some examples of going through the process of sketching graphs, but I don't think we have time to go through each one of those. In general, like I said, what I'm going to be looking for if I give you a sketch a graph on a quiz or a test, I would say, generally I'm going to say, sketch the graph of this function include in your analysis the domain and range, intercepts, asymptotes, maximum, minima, that kind of thing. Yes.
Will we get a calendar for like an outline of the function?
Oh yes, that is. That is on my website. I can print one out for you, or you can just go to the website. So let me show you where that is on my.
Yeah.
Here in the handout section, I already have it posted up. We have the assignment sheet for this chapter and the schedule.
Wait, that's today.
This is today? No, this is today.
Wait, what? Yeah, that's today.
It's not due till Thursday, right? Right.
That's so. Just change all the days but Wednesday.
So let me put up the assignments. In general, plan on having an assignment every day. What I would suggest on these is maybe not necessarily do every single one, but numbers 1 through 4 and 6 are kind of like the ones we just did on the board. So I would suggest doing those. Pick a few out of here. Number 34, I wanted to talk about that quickly. Number 40 and 44 are trig functions that you're analyzing. Look at example 6 in your book for an example of doing that. 47, 48, and then numbers 58, 59, and 69 are kind of conceptual problems. Explain why this would happen. So there's not a lot of computation. So I would suggest doing these. Pick some out of these to do. These are trig functions. Number 34 involves an absolute value function that you need to sketch. How do you take the derivative of an absolute value function?
Whatever goes negative, you make it positive.
We can do that. If we wanted to actually find the derivative of an absolute value function, you guys know how to do the derivative of an absolute value function? What's another way we can write the absolute value function? Square root of x squared. Absolute value of x is the same as square root of x squared. So if you write your function like this, then you can actually take the derivative of the absolute value function and do the analysis out. But you can also flip it wherever it's next.
Just do the square root of that function squared.
Yes. And then you can take the derivative. And then when you see that quantity again, that square root of that function squared, that turns back into the absolute value of whatever. Okay? All right.
All right.